So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Andrew Yuan, who will tell us about Unified Framework for Quantum Code Embedding. So Andrew has bachelor's degrees in math and physics and an MA in math from UCLA and a PhD in physics from Stanford, where he specialized in statistical mechanics. As a current postdoc at UMD, Andrew recently developed interest in quantum error correction, and his interest is driven mainly by mathematical proofs that involve locality, which naturally leads to work on quantum LDPC codes. So Andrew, the floor is yours.
Okay. Yes. Thank you for the introduction. Okay. So today I'm going to talk about a framework that I developed. The top right corner is the archive reference for those who are interested in the details. But today I'm just going to go for I'm not going to go into the abstract details, but rather just an overview of what the framework should look like. Okay. So the main result is just to introduce the general framework so that when modifying a CSS code by adding ancillas, when does that preserve the logical subspace? So some examples, which I'll talk in detail, include the following: code concatenation, embedding LDPC codes into Euclidean space, which the basic idea is that even though a general LDPC code defines a local graph structure, but for physical implementations, it's much more feasible if the parity checks and qubits can be arranged in a cubic lattice in some dimension. There's also quantum weight reduction, which is basically the process of adding ancillas so that we can reduce the weight of checks. This is, of course, closely related to logical measurements. Specifically, since logicals are usually very large in weight, it's difficult to measure them directly in a fault-tolerant manner. Therefore, one idea is to arbitrarily add a logical as a stabilizer check and then reduce the weight so that the logical can be measured indirectly by multiple small weighted checks. Okay, so let's start with code concatenation. The reason is that the framework can be regarded as a generalization of concatenation, so it's important that we understand the simpler case first. So on the level of states, code concatenation starts with a given CSS code A and another code B. The physical qubits of code A are then replaced by the logicals of B to obtain this output code C. In this case, it's natural to suspect that the input code and output code have isomorphic logical qubits. Now, just like any other stabilizer problem, it's usually more convenient to think about the problem at the operator level. So in this case, code A could have some parity checks, some X-type and Z-type parity checks specified by the parity matrices. And then code B has some logical representations, which I denote using the X bar and Z bar notation. So in this case, the process of replacing physical with logicals is equivalent to replacing the physical poly operators with the logical poly operators of my code B. With that in mind, my output code C now has checks that include those of B, but more importantly, these modified checks of A, which I have just replaced each poly operator with a logical operator. Now, in this case, we see that if code B has a large distance, then the parity of checks of C may be very large, and thus not even LDPC, even if the input codes are LDPC. This is quite the problem, since LDPC is usually necessary to guarantee fault tolerance for asymptotically large codes. Therefore, I need a generalization to accommodate more complicated cases. Okay, so just as a side note, I want to mention that this is usually not a problem for conventional code concatenation. This is because usually the code A is chosen to be a small, like O1 size, and code B are just copies of A, one for each physical qubit. So in this case, because code A can correct single qubit errors, the error rate is suppressed after this concatenation process. So it goes from p to p squared, while the check weights only increase by a bounded constant. If I were to iterate this process, L times, then the error rate would be suppressed doubly exponentially, while the check weights would only increase exponentially. So this means that if I wanted to reach an error threshold like epsilon, the check weight would only increase logarithmically. So, it's somewhat a problem, but not really, because it's only a logarithmic increase. Okay, now, to obtain a generalization, we need a bit more technology. So just like how we went from quantum states to operators, now we further abstract and consider chain complexes. By definition, just to review, by definition, a complex is a sequence of vector spaces with these linear maps called differentials. And the crucial condition is that if you do matrix multiplication of the linear maps, then it always has to give you the zero map. So partial 1 times partial 2 equals 0. What this means is that the image of partial 2 has to be in the kernel of partial 1. And this means I can define the quotient space, usually referred to as the homology. To relate back to CSS codes, we can define the differential maps via the parity check matrices as follows. So in this convention, I have kind of chosen A2 to be my vector space generated by my Z checks, my A1 to be the qubit space, and A0 to be my X checks. The differential map is then specified by the parity matrices, HX and HC transpose. So using this convention, it's quite easy to see that the first homology is going to be equal to the equivalence classes of all the type logicals. So as you can see, the complex now contains all the necessary information of a CSS code. Okay, now technically, if I wanted to be comprehensive, I would also have to consider co-complexes or co-chain complexes, where the cohomology is then defined so that it's equal to the X-type logicals. But for chain complexes, there is this theorem telling you that cohomology and homology are isomorphic, and so I won't have to care about that. At least, so basically, for the rest of this talk, I'm really only going to focus on one type of logicals, while the other type can be obtained through an isomorphism. Okay, so coming back to code concatenation, we now have three equivalent ways of describing the process. The first one, of course, is at the quantum state level, where we replace physical qubits with logicals. The second is at the operator level, where physical polys are replaced by logical polys. And finally, we are at the complex level, where we have the requirement that A1 is equal to the first homology of code B. Okay, so now admittedly, there's a bit of a jump in logic here, but remember that A1 corresponds to qubits of code A, and the first homology corresponds to the logicals of code B. So hopefully the intuition is somewhat clear. Now, as we mentioned previously, this isn't quite enough. So a natural generalization is just to pick independent CSS codes, so C2, C1, C0, and require that their homologies are equal to the Z checks, qubits, and X checks of my input code A. Okay, so just to summarize, what the framework basically tells you is that given a CSS code written in the form of a complex, I want to find independent CSS codes or complexes such that each vector space is now replaced by the homology of the given code. I then somehow glue these independent CSS codes together, and then I want to show under what general gluing conditions can I show that the input code and output code are isomorphic, and when is the code distance preserved? Okay, so of course I'm being kind of vague here, right? Like what does gluing actually mean? What are the compatibility conditions of gluing? And of course, the more interesting problem is, why does this solve the LDPC problem? Why are the checks now LDPC, basically? Okay, so I'm gonna these questions I'll answer them shortly. Okay, so starting from the first question. Why does this generalization help with the previous LDPC problem? Well, to see this, instead of providing, the explicit details, let's look at a particular example. So consider the layer code construction, which was discovered by Dominique Williamson and his student Nadine Bassman, where they basically provided a method to embed any LDPC code into three-dimensional Euclidean space. In particular, if the input code is a good LDPC, which basically means that the quantum dimension and code distance scale linearly in system size, then the output code is going to saturate the BPT bounds, which is like a theoretical upper bound of scalings in Euclidean space. Now, since the construction works for any CSS code, let us just consider a simple example where code A has two checks, XXX and ZZI. So what this construction really does is that it replaces each physical qubit with a surface code, so that the Z bar, or the Z logical, is in the Z direction, denoted by this red line, and the X logical is in the X direction, denoted by this blue line. Because there are 3 qubits, I replace each physical with a surface code, so there's now 3 independent surface codes, which basically means which also which tells you that the homology has dimension 3. Now, because there is only one Z check, I replace that Z check with another surface code, but now with rough boundary conditions, so that this red layer doesn't have any internal logicals. But it does have a global homology, or a redundancy, basically. So the homology of C2 is 1, which is equal to the number of Z checks. Okay, so you can do the same thing for the X check and replace each X check with a surface code, but with smooth boundary condition. So that, again, the code does not have any internal logicals, but has one-dimensional zeros homology. So again, you can see that this example satisfies the general requirement that the homology of each independent code is equal to the vector space of my input code A. Yes, satisfies this condition. Okay, so currently, one can think of the layers floating in three-dimensional space and thus are not interacting. Therefore, the next step is to somehow glue these layers together. So let's treat the gluing process one step at a time. Because the Z checks of the input code act on the first 2 qubits, the red layer has to interact with the first 2 qubit layers by acting on the Z logicals of the qubit layer, so denoted by these red lines. Specifically, since the layers represent a bunch of qubits and parity checks, so each colored layer is a bunch of qubits and parity checks, what we mean by modifying it is just modifying the stabilizers near the intersection. So only stabilizers near the red lines are going to be modified, while stabilizers away from it are still the same. Formally, one can think of this as a chain map between complexes, which you can just think of as a mapping that satisfies some compatibility conditions. Okay, so similarly, you can the X checks of the input code acts on the 3 qubits, and so the blue layer must interact with all 3 qubit layers. Again, this means modifying the check near the intersections, which is formally captured by a chain map between the complexes. Okay, finally, there's also a defect between the red and blue layers. Specifically, in order for the output code to be a stabilizer code, one needs to introduce a defect between the red and blue layers. Basically, since X and Z checks commute, they must act on an even number of qubits. So in this example, they act on both the first qubit and the second qubit. And because there are an even number of common qubits, they can be paired up into pairs. And then between each pair, we can draw a string defect connecting the two. So this green line represents that defect term. Now, of course, you can write this down more formally and show that this defect term has to satisfy the algebra of a chain homotopy, but we won't go into the details about exactly what that means. Basically, all you really need to know is that there are three gluing maps that have to satisfy some compatibility conditions so that you can use the homologies. Okay, so just to summarize, we need to glue the corresponding complexes together in a compatible way. Putting everything together, we have this three-dimensional diagram. Notice that the output is now LDPC, and thus the generalization solves the previously mentioned problem. Specifically, by utilizing the homology, we can break a large weighted check into smaller pieces. Basically, the large weighted check is now broken down into a bunch of checks in the red and blue layers. Okay, because the complexes are glued in a compatible way, we can prove using our framework that the logicals are isomorphic, where C is the output code and A is the original input code. As an example, consider the logical ZIZ of A. One possible representation of the logical in my output code C is shown by these squiggly lines. So where the color of each segment indicates which layer it's on. Now we'll come back to this layer later, but notice that the logical representation has support on all three colored layers. This is not very nice since it makes bounding the code bounding the code distance very difficult. So later on, we'll introduce a cleaning lemma so that we can clean some of the segments so that it's easier to bound. Okay. So now that we have an explicit example in mind, we can state the framework a bit more formally. So previously, we started from a code A, input code A, and based on some algorithm, defined an output code C. But this time, let's think in reverse. So forget about code A, and suppose that we are given a code C that is constructed by gluing complexes together in some compatible manner. So basically, we are starting out with the three-dimensional diagram. We can then prove that the following is also a complex. Note that the vector spaces in the complex are now replaced by the homologies of each independent complex, while the gluing maps now serve as the differentials. So the GQZ, GXQ, the bracket notation are just to tell you that we are passing through quotients, so that we can define them on homologies. Of course, this process is illustrated by the figure on the right here. Finally, if C2 and C0 do not have internal logicals, so basically the red and blue layers do not have internal logicals, then we can prove that the input and output code have isomorphic logicals, as given by equation 3. Okay, so technically, I have already finished stating the main result of this paper, but since there's still quite some time left, I think it would be beneficial to go over some more examples and provide some intuition on how the framework can be used. So to some degree, the complexes in the layer code construction are somewhat straightforward. You can kind of tell which layers represent which complex. But maybe there are examples where you can't choose C2, C1, C0 obviously. And you have to go through a bit more work to find out which parts represent C2, C1, and C0. So let's consider the following work, which came out at around the same time as the layer code construction. So roughly speaking, although their method is different, the results are similar, in which they show that any CSS code can be embedded into Euclidean space in 3 dimensions or higher. And in particular, they also have the result that if the input code is a good LDPC, then the output has to saturate the BPT bounds. Now, because their embedding works for any CSS code, let's just consider the simple example of a toric code. So in this diagram, the gray dots correspond to the qubits, the black corresponds to the X checks, and the dashed dots or white dots correspond to the Z checks. Now, since the parity checks commute, the common support of qubits in an X check and a Z check must be even, and so they can be paired up arbitrarily to form squares. This is kind of similar in spirit to how the layer code construction had to pair up qubits when introducing string defects. In this case, the authors subdivide each square from O1 number of qubits and parity checks to L square parity checks. And then it was proven that for sufficiently large L, the subdivision process can be mapped into Euclidean space. So on the right figure here, we basically show the shaded regions means that there are more parity checks and qubits inside that we don't actually show explicitly. So in this case, it's kind of hard to tell what exactly C2, C1, C0 are. So I'm just going to tell you the answer. So C2 are all the blue regions. So that includes all the shaded parts, the lines, and also the dots, the dots. C1 is all the gray lines and dots, and C0 are just the black dots. So as you can see, not only they are not obvious, they're not even symmetric, even though the construction itself is symmetric. So basically all this example is just to tell you that C2, C1, C0 are not necessarily obvious, and you might need a bit more effort to find them. Okay, a more simple example would be the toric codes. We know that the logical qubits of a toric code depend on the underlying manifold and not the exact way we discretize the manifold. This means that a toric code defined on a square lattice should be isomorphic in some sense to the toric code on a hexagonal lattice. So if we want to use the framework to show that these two codes have isomorphic logicals, then one way is to define independent complexes as in the following case. So C2 are the faces, C1 are the gray lines, and C0 are blue lines and dots. So basically what this diagram is trying to tell you is that if I squish each blue line into a dot, then the hexagonal faces become squares. And then the framework provides an isomorphism between the two. Okay, so the main reason I quickly reviewed these two examples is to show that independent complexes may not be very obvious. Therefore, I want to rewrite the hypothesis of my theorem in an equivalent manner. So in this case, all we need is that the complex C, or my output code, has vector spaces that can be decomposed into a direct sum composition, and then the differential is triangular. So these two hypotheses are exactly equivalent, and the compatibility conditions are given by the condition that the code C is a complex. So basically, the differential squared has to be 0 is exactly what the compatibility condition is. Okay, so these are just two equivalent formulations of the same hypothesis. So they're telling you the same thing. It's just different ways of thinking about it. Okay, so another point I kind of want to address is what is the intuition behind H2 and H0? For the first homology, we can look at the toric code and notice that the logicals are non-contractible loops. So a natural question is whether we can obtain a similar intuition for H2 and H0. Now for simplicity, I'm only going to focus on H2 because given any complex, its cochain complex obtained by transposing the differential maps gives you, this relationship. Basically, the zeros homology of the transpose is isomorphic to the second homology of the original complex. So basically, understanding H2 gives you some idea of H0. So basically, you only need to understand one or the other. Okay, so let's revisit the simple example of the layer code construction. Now, because I'm focusing on H2, I really want to focus on the red layer. What our framework tells us is that the complex must have a homology that is in one-to-one correspondence with the Z checks. And then I also need that C2 has no internal logicals. So these are the two conditions that I want to satisfy. Now, for the layer code construction, this was satisfied by using a surface code with rough boundary conditions. But a more careful examination shows that such boundary conditions turns the toric code into a cell complex. So with vertices V, edges E, and faces F. And then the linear maps are defined by the usual adjacency relations. Now, in this case, the cell complex has a second homology that is equal to the cell complex has first homology equal to all the cycles, but because these cycles are generated by all the faces, the homology has to be 0. And the second homology of a cell complex is given by the connected components of the graph. So in this case, because the square lattice is connected, that means there's only a single connected component. And so each layer is in one-to-one correspondence to the Z checks. Now, from this perspective, there are then some natural generalizations. Basically, any cell complex with a single connected component and no non-trivial cycles can be used as C2. So, maybe, for example, maybe expander graphs could be used since they have very nice expansion properties. Now, with that said, there is still some subtlety in choosing a nice cell complex. So let's consider the simple example again. In this scenario, each qubit was replaced by a surface code so that the Z checks are now expected to act on the Z logicals of corresponding surface codes. Now, since the logicals form a string, this induces a graph structure as indicated above. So basically, by replacing each physical qubit with a surface code, this procedure induces a graph structure for neighboring Z checks. So in this case, sorry, for one moment. Sorry about that. Yes, so what I was saying is that by replacing each physical qubit with a surface code, and because the Z checks have to act on the Z logicals of my surface code, this induces a graph structure for my Z check. So in this case, my Z check has the graph structure of two disconnected strings. Now, if I were to just use these two disconnected strings as my cell complex, then as you can see, there are multiple connected components. So that doesn't quite satisfy my first condition. And in this case, there are no non-trivial cycles, but more generally, that's always a possibility that you have to consider. So what we have to do is to find a connected graph that contains this induced graph, and also find faces to remove any possible cycles. So in this scenario, my graph would correspond to the red layer, which contains the induced strings, and also is connected and has no non-trivial cycles. Okay, so this was done through the layer code construction, but how would one do this more generally? Now, one interesting idea that first appeared in the context of weight reduction was the idea of coning. The idea was initially introduced by Hastings, but then further optimized by Xu and others. So roughly speaking, the idea goes as follows. If we start from some induced graph that could have come up by replacing physical qubits with some surface codes or other codes, the graph is not necessarily connected and also has, could also have cycles as shown here. Now, in this case, we could replace this induced graph with this cone-like structure. So basically, I have added this extra vertex, the red dot, and added edges that correspond to connecting the red dot with the original vertices. And then I also add faces that correspond to the connecting the red dot with the edges of my original graph. So as you can see by the shaded region. In this case, you can then see that my cone structure is now connected because all vertices are connected to this extra red dot. And it also doesn't have any trivial cycles. For example, in this example, my original graph had this unique loop cycle here. But as you can see, in my cone structure, the cycle is now the boundary of all the vertical faces. So basically, if I were to have, because my vertical faces are in my cell complex structure, it generates that cycle, and so it's not. And so that original cycle is non-trivial now. And it's also clear that my original graph is embedded in my cone structure. So the cone basically satisfies all the necessary conditions or all the sufficient conditions that we were looking for. And now, the only problem here is that the naive cone, basically adding a single extra point, is not going to be sparse because the extra vertex connects to all vertices of the original graph. So the basic result of Hastings and Xu is to somehow sparsify these cones. Okay. So now that we have some intuition of the individual complexes, let's talk about the codistance. Specifically, when is the codistance of our new construction bounded below by the original one? Okay, so again, let us consider the example of the layer code construction. We know that ZIZ is a logical of A, and the following squiggly line indicates a general representation of the logical in the output code C. Basically, what I'm saying is that a general logical could have support on all three colored layers, so C2, C1, and C0. However, by using our framework, we can prove a cleaning lemma, which states that there always exists an equivalent L prime that is only supported on C1 and C0. So in this example, what you would do is that you first get the logical representation, and you apply stabilizers that correspond to this red region. By applying the stabilizers corresponding to this red region, the red segment is now cleaned, and so what we're left with is only the gray and blue segments. So L prime is only supported on C1 and C0. Now, because L prime is supported on C1 and C0, its restriction to C1, so the gray layers, have to correspond to logicals of the surface code. And because each portion, and because the surface code has distance, greater than L, we can bound L prime based on, the distance of the surface codes and the distance of my input code A. Now, although bounding, L prime is nice, to get the actual code distance, we need to bound a general representation. And this ultimately boils down to the expansion property of the red layer, or C2. So basically what I'm saying is that as long as this inequality is satisfied, then the general representation has to be lower bounded by the clean representation. So what this inequality basically tells you is that the left-hand side is the boundary operator of my C2 layer, so which is represented by the red boundary, and the right-hand side corresponds to how this layer is glued to the qubit layers, so which is shown by the gray aligned segment. So as you can see, the layer code construction satisfies this nice property because the gray segment is always going to be smaller than the boundary of the red region. But more generally, if we only allow the gluing map to be sparse, then this inequality is a boundary and bulk inequality. So we require that the boundary must be greater up to some coefficient than the bulk region. And so expander graphs would work really well in this case due to their nice expansion properties. Okay, so just to summarize, we introduced a framework to explain how logicals are preserved under ancillas. And then we further provided some intuition behind the framework, we further provided some intuition behind the framework and why it may be useful in unifying different directions. Now, admittedly, nothing new is. I haven't told you anything new, any new results. It's only a framework that unifies existing results. So whether it can be actually used to come up with new results is for future work. Okay, thank you. That's the end of my talk.
Okay. Right. Thank you very much for some very interesting ideas from this talk. Right. So I guess we are actually, yeah, there's plenty of time for questions and discussion. So I don't know. Yeah, so if anyone in the audience is has some questions, clarification, you may unmute yourself and ask. Don't know if we have particularly people who's doing error correction here. I myself am not really familiar with all of the details. Yeah. But I'm curious, so because you've initially motivated this kind of as starting from generalization of this concatenation.
Mhm.
So is the concatenation also in the framework? So I guess it will be there, right? In a
Yes.
simple
Yeah.
way.
Right. So let me try to share this one more time. Here. So the code concatenation process is just this is basically. So I hopefully the first two equivalent methods are somewhat clear. You're right.
Mhm.
You're replacing physical states with logical states, and that's the essence of code concatenation. And then each step is just being more abstract, right? So from states to operators, and then finally to complexes. So I'm basically replacing the homology, the qubit space A1 with the homology of code B. And this is of course a particular case of the generalization below, right? I'm replacing now each vector space with a homology of a different CSS code. So in this case, the particular example would be replacing B with C1. So if you want to match notations.
Mhm. Okay. Okay, let me see if there's anyone with a question or comment. I suppose, yeah, Minsha would have maybe some questions if he's around.
Yeah, Miu probably has is much more familiar with all this stuff.
Yeah. Okay, maybe just kind of like one naive question about the last part.
Last part.
So like when you were using this kind of like, I guess you're calling it cleaning lemma.
Oh yes, clean.
But this is only, so the reason that you wanted to do this is because like, yeah, you cared about like the sparsity, right? I guess in some sense,
Oh, so I guess
somewhere, or is it for a different reason?
right. So the point is that I want to bound the weights of a logical
Mm.
representation, right? So if I were to look at a general representation, so the left-hand side, it has it has qubits on all three types of layers, right? But if I were to clean it so that it only has, a support on the gray and blue areas, then, the restriction to the gray areas have to be logicals. So if you look at the gray lines, they must be logicals of my surface code. And then, I know the lower bound of these gray lines. Each gray line has to be at least, the code distance of my surface code, so DC1. And then you just have to count how many gray lines there are. And then that's given by the code distance of my input code A. So once you clean it, you have an algorithm to kind of like lower bound the weight. But for a general representation, you can't do that because in the general representation here, the gray lines are not necessarily logical of anything. Or neither is the red segment or anything like that. So there's no clear way to bound a general representation. Only after you clean it, the gray lines are now, logicals of my layer codes.
Okay.
And then the question is, how do so I can bound the cleaned representation, but how do I relate it back to the general representation? And that's where you need this expansion property. Which seems to be so for the layer code, there's a nice construction for this, but more generally, expander graphs have this nice expansion property. So the cleaning lemma would be applied straightforwardly for expander graph.
Right. Okay. Yeah, I spent too much time on my questions. So anyone else wants to discuss? Okay, I don't see anything here. Right. Yeah. So I guess if there's no more, I think we can sort of adjourn earlier. So yeah, I'm waiting
Yeah.
if Mincho will actually sort of show up. But he's kind of busy with some kind of events. We have like a company event next week, and they're kind of like rehearsing things. Yeah. So
I see.
yeah.
I'm actually kind of curious. Is this like an online seminar? Because I feel like I don't see anyone, in a conference room or anything like that.
Yeah, it's online because like most of the people in our group are actually like in different places.
Ah, I see.
So yeah, so the seminar is arranged to be online. Yeah.
Okay, that makes sense. Yeah.
Hello. Yeah, sorry.
Oh.
I was called to into another meetings. Sorry about that. Yeah.
No worries.
Okay.
I feel like you're already very familiar with all this, so you don't even need to listen to the talk.
No. That's why I'm interested in your talk. No, this is exactly the topic that I work a lot and I wanna. Yeah.
True. Yeah, some of the examples were, based on your work. Though I didn't really go into details because your works are much more complicated than the layer code construction. Okay. Well, thank you for the invitation. I'm always happy to discuss more if anyone has questions or So send me an email if you're interested.
Yes, yeah. I mean, okay, you got ahead of me. I usually end by asking like if we have like further questions and this
Oh.
like wanted to discuss. Hopefully we can just contact you directly, through the email.
Sure.
Yeah.
Sounds
Okay.
Mhm.
Because you stopped this page. That is like our very recent paper. Yeah. Honestly, I have been. I think I complained this to Hiccup. So this is actually the submission that my submission to QIP, and this I like this work the most. This weight reduction work, but unfortunately it got rejected. And and
that's so unfortunate.
yeah. And I was a bit upset because like there's even like one review with only one sentence, like this is incremental and it's basically hasting. But yeah, so what do you think about this work? If I
I think it's very interesting, especially how symmetric it is. In Hastings' work, there it's not really symmetric in the X and Y.
all steps, 5 steps, and each step is getting more and more complex than previous step.
Yeah. I guess the only thing that's at least hard for me to understand is that some of the results are kind of implicit, or like they kind of use some previous results, and it makes it hard to, I guess, understand what's happening here.
I see. Yeah, that's true. Because this was built on our subdivision work that we used in geometric local quantum LDPC. And I think I also complained about the writings to Xingjian and Dingjun. So yeah, that's true. Okay, we probably need to make the writings and make it more readable. Yeah. Thank you for the feedback.
Yeah, no worries. Especially the part about so I guess I was actually I was reading your paper in detail, and I was looking how to fit your stuff into the framework. And I think everything, okay, if you take the time, it does fit into it. But the part that I couldn't quite fit is that how do you prove this expansion property? Like this part, like I think you actually quoted the Kleene lemma, but I don't quite see how you prove it. Maybe it's implicit or something, but I couldn't tell.
Yeah. Expansion is, I think it's a bit high level, but I think the deep down it's from another earlier papers on this good LDPC and the expansion properties, especially from that type of argument. Yeah, so
I see.
yeah, I think we probably need to significantly include a lot of like discussions. But I thank you for your feedback. I would pass on to the student who write this paper. Then
Sounds great.
yeah, thank you.